In this video, we're going to quickly review the idea of self-inductance and the back EMF induced across an inductor when the current changes. Then we're going to apply the formula for the induced EMF to an RL circuit. In other words, a circuit containing both a resistor and an inductor. We're going to cover two different cases for the RL circuit. First, we look at an RL circuit that's just been switched on. We derive a formula for the current as a function of time, and we derive a formula for the half-life of this current. In other words, the time it takes for the current to get to half its maximum value. Next, we look at an RL circuit that starts at its maximum current value and gets switched off. Again, we'll derive a formula for the current as a function of time and the half-life of that current. Finally, we take a look at the case of a square wave signal applied to an RL circuit. In other words, we're just repeatedly switching it on and off. And we focus on how we can use the output of an oscilloscope to determine the half-life of the current and then calculate the inductance of the circuit. As a quick reminder, the idea of self-inductance is that an inductor or a coil of wire is resistant to changes in current because of Lenz's law. And I'll post a link real quick to where Lenz's law was first discussed. For example, if we close this switch and turn on the power in the coil that you see in the picture, current will begin circulating around these turns, and using the right-hand rule for the field generated by the current, we see that the magnetic field will curl to the right within the coil because my fingers on my right hand curl to the right when I place my thumb in the direction of the current. Well, Lenz's law says that when new magnetic field lines pass through the turns of this coil, an EMF is induced to oppose the change in magnetic flux. This means the induced EMF is in the opposite direction of the applied EMF, and acts in a direction to create magnetic field lines pointing to the left in order to reduce the change in flux. This induced EMF is called back EMF, and it always opposes the changes in the current through an inductor coil. This means an inductor slows down the increase in current when we turn on the power source, and it also slows down the decrease in current when we turn the power source off. So you can think of inductance as a kind of current inertia. Just like a larger mass means more resistances to change in speed, a larger inductance means more resistance to changes in current. Next, we want to quantify the back EMF produced in an inductor. I'll post a link to the video where this was first derived from Faraday's law, but the conclusion was basically this. The induced EMF was given by negative L times delta I over delta T. L is called the self-inductance of the coil, or simply the inductance of the coil, and delta I over delta T is the rate of change in the current. So that's taking care of the fact that a faster change in current produces a larger back EMF. In order to make progress on analyzing RL circuits, we're going to need the instantaneous version of this formula. So we think about this in the limit of a small time interval, and that delta I over delta T, that becomes a time derivative. So there's our formula for the back EMF produced by an inductor, and we're ready to apply this thing to an RL circuit. So here's our first RL circuit, and we're going to switch on the DC power supply with a voltage of V when we close this switch. Before we get into the math, let's think about how this should go. The inductor is going to resist changes in current by inducing a back EMF, but it ultimately loses the battle. The current starts at 0 and then increases over time to some maximum value, and what the inductor has done is just slow down the process of reaching this maximum current. After enough time goes by, we can say the circuit reaches a steady state, or a constant current. When the current becomes constant, the inductor no longer has changes to resist, and it will provide no resistance to the flow of current. In other words, the circuit eventually becomes equivalent to a simple power supply with one resistor, and Ohm's law tells us that the steady state current will just be V over R. So I can say it like this: eventually I is V over R. In other words, when the current levels off, the inductor isn't doing anything. And we're going to come back and check that once we figure out what our current is as a function of time, and we're going to make sure that our function is behaving correctly. Now to get into the derivation, the simplest way to think about it is to just look at the voltage across the resistor. So I'm going to label a couple nodes in the circuit, one above the resistor and one below the resistor that's actually connected to ground. Well, the voltage across that resistor is the combination of my positive voltage from the power source and the back EMF induced in that inductor. That inductor is attempting to reduce the current in the circuit, so it's going to produce a negative voltage and reduce the total voltage across that resistor compared to just the power source itself. So I start by just looking at Ohm's law applied to the resistor, and I'm just going to call it V net. So the net voltage across that resistor is equal to I times R. And the net voltage across that resistor is the voltage of the power source minus the back EMF, L, di dt. We should take a moment to make sure that the signs make sense here. So di dt, that's the rate of change in the current. That's a positive number because the current is increasing, and that means putting a minus sign out in front here creates a negative voltage. So our back EMF is reducing the total voltage as it should. Now what we're looking at is actually a separable differential equation. And I'll post a link real quick to the video where I first introduced these things. I have the derivative of I in this equation, and I have I itself in this equation. And what I can do is arrange all the I dependents on one side of the equation, everything else on the other, and we'll be able to use an integral to solve the equation. So I'll go ahead and start by subtracting V from both sides and then dividing both sides by negative L. We can distribute the minus sign inside those parentheses. And now I'm going to divide both sides by V minus IR. At the same time, I'm going to multiply both sides by dt. Now that the variables are separated, we just put an integral sign on each side and integrate. And on the left-hand side, I have to deal with the chain rule backwards because my integration variable I has a constant stuck to it of negative R. If I can get the derivative of this denominator up in the numerator, that takes care of setting me up to do the chain rule backwards. And the derivative of V minus IR with respect to I is just negative R. Well, we're free to just throw that constant into the numerator, provided we compensate out in front of the integral. Now that negative 1 over R out in front becomes a spectator for the next step. And what I'm integrating here is 1 over some function multiplied by the derivative of that function. This gives me the natural log of that denominator. On the right-hand side, I'm just integrating a constant dt. Well, that becomes the constant 1 over L multiplied by t. And then we need to throw in an arbitrary constant of integration somewhere. So I'm going to put a plus c on this. Now we multiply both sides by negative r. And in my first term on the right-hand side, I get a negative r over L times t. And then we have plus r times an arbitrary constant c, but that just produces a new arbitrary constant, so I'll just call that c. Then I undo the natural log, and I end up with v minus ir equals e to the negative r over L times t plus a constant c. Well, I could write the right-hand side of this as e to the c multiplying e to the negative r over L times t. And e raised to an arbitrary constant is just another arbitrary constant. So the right-hand side, we could just call that c e to the negative r over L times t. Now, ultimately, what we're after here is solving for I as a function of time. So I'm going to subtract v from both sides and then divide by negative r, and I should be able to isolate I. Now we apply the initial condition to nail down that arbitrary constant. The initial condition is that I of 0 is equal to 0. I had no current initially. So if I plug in t equals 0, I get I equals 0. So I is 0. When t is 0, well, e to 0 is just 1, so I end up with a c minus v in these parentheses. I can divide out the 1 over r out in front. And in order for this to be 0, I see that c has to be equal to v. We plug that c into our current function. I'm replacing this with a v. And I can factor the v out as I go, and I end up with a negative v over r times e to the negative r over lt minus 1, and this would be a bit nicer if I just distributed the minus sign. And I get v over r times 1 minus e to the negative r over lt. Before we move on, I want to look at some limiting conditions to make sure that they check out for this current function. So the first thing I'll look at is just checking that I of 0 is actually 0. When I plug in t equals 0 into this function, I get v over r times the quantity 1 minus e to the 0, but e to the 0 is 1, and 1 minus 1 is 0. So that checks out. The other thing I want to check out is that the large time limit of our current function gives us the maximum current that we're expecting, which was v over r. So does it work? I take the limit as t goes to infinity of v over r times the quantity 1 minus e to the negative r over L times t. That's a decaying exponential function, and when t gets very large in that exponent, I have e to a large negative power. In other words, that's approaching 0. So the result of the limit is just going to be the leftover v over r out in front, and that one checks out as well. Now that we've obtained the current as a function of time for this circuit, there are a couple more things to accomplish. First, we want to check out the graph of this current to see if it makes sense. we see that I starts at 0, and then it eventually levels off to some maximum value. That maximum value is the steady state current that we already said is given by V over R, because when the current levels off and stops changing, the inductor stops producing back EMF, and our circuit becomes equivalent to a simple power source with one resistor. It's convenient to give the name I naught to that maximum current, and we can use that to clean up the appearance of the formula. So notice in the formula at the bottom, I had a V over R out in front. Again, V over R is just I naught. So I'm going to rewrite this as I of t equals I naught 1 minus e to the negative R over L times t. The next thing we do to clean up the appearance is that we can define a time constant so that this function can be rewritten as I naught 1 minus e to the negative t over tau, where tau is the new time constant. And this means that tau must have been L over R. Finally, when we see exponential behavior, it's useful to talk about the changes in the current in terms of half-life, or the time to reach half the maximum value. We can visualize this in the picture of the function by placing some cursors into it. Here's the maximum current of I naught, and then the minimum current, of course, was 0. So I can place a third cursor at the halfway point. There's the current reaching half its maximum value. Well, that means this time, the time from t equals 0 to the point where I gets to half its maximum value, that's the half-life, which we'll call t with a subscript of 1/2. To figure out what the half-life is, we look at our current function, and we say when t is equal to 1 half-life, I is equal to 1/2 its maximum value. In other words, 1/2 I naught. So to start the quick derivation, we just say 1/2 I naught, that's the moment we're interested in, is equal to this function evaluated at t equals 1 half-life. So I end up with an e to the negative t 1/2 over tau. Now those max current terms cancel out. I'm going to subtract 1 from both sides, and I get negative 1/2 is equal to negative e to the negative t 1/2 divided by tau. The minus signs cancel at this point, and I can take the natural log of both sides, and I get natural log of 1/2 is equal to negative t 1/2 over tau. Well, 1/2 is just 2 to the negative 1 power, so I can pull the negative 1 out using the properties of logarithms and call this negative natural log 2 is equal to negative t 1/2 over tau. The minus signs cancel, and I arrive at a formula for the half-life. T 1/2, the half-life, is tau natural log 2. We could also state that in terms of L and R by replacing tau with L over R, and I get L over R natural log 2. So the major takeaway here is that the time for this current to reach half its maximum value depends on the inductance and the resistance in the circuit. Our next major goal is to determine the current as a function of time if we turn the power source off. So this time our initial state is the steady state in which I is equal to V over R. We then remove the power source, but current is still allowed to flow. In other words, we shorted out the power source. So in our picture of the circuit, the power source is simply gone. Current is allowed to continue flowing clockwise for some amount of time until it winds down to 0. Again, we analyze the circuit by just looking at the voltage across the resistor. And again, I'll emphasize that our initial state for the current is current flowing clockwise through the circuit. We'll call that I naught, and that's V over R, where V is the voltage of the power source that was there before we removed it. Well, this time, the back EMF induced by this inductor is going to try to keep the current moving in that clockwise direction. In other words, it's fighting the reduction in the current. So this time the inductor is going to produce a positive voltage over this resistor R. And in fact, it's the only thing producing a voltage over R. So we can start again, just as a reminder, with Ohm's law. And then we realize the only thing applying a voltage to this resistor is the inductor. And that's given by negative L di dt. And again, I want to check the signs to make sure they make sense. Di dt is a negative quantity. And with that minus sign out in front, that means this voltage is positive. In other words, it keeps the current flowing in that original clockwise direction. So that looks good. This time it's actually easier to separate variables. I'm going to divide both sides by I. I multiply by dt to move that over to the right-hand side, and I divide by negative L, and I end up with a negative R over L dt on the right-hand side. We then integrate, find the antiderivative of each side. This gives me a natural log of I on the left-hand side, and a negative R over L times t plus an arbitrary constant c on the right-hand side. We undo the log and express it in terms of an exponential. So I have I equals e to the negative R over L t plus c. We do the same trick as before where we say, well, e to the c is the same as just some other arbitrary constant. So I can rewrite this as ce to the negative r over lt. I then plug in my initial condition that I of 0 should be V over R, where V was the voltage of the original power source. And when I sub in t equals 0 to evaluate I of 0, well, that's just C. So I figured out C is actually V over R, and I obtained my current as a function of time. So that's going to be V over R e to the negative R over L t. Now that we have our current as a function of time, we should make sure that it's making sense in some limiting cases. One of these is to just check that I of 0 is V over R. So when I plug in 0 for t, I get a V over R e to the 0, but e to the 0 is just 1, and I get V over R, and that checks out. Secondly, the large time limit of I should be 0. Because we remove the power source from this thing, all the energy is eventually going to dissipate and the current will go to 0. So we take the large time limit of I of t. That's just the limit of a decaying exponential function. So I have an e to a negative power, and as t gets large, that becomes e to a large negative power, and that approaches 0. So that checks out. So here's a picture of this decaying exponential current function. It starts at this maximum value that we said was V over R, where V was the original voltage of the power source before we turned it off. And I see the current dropping with this exponential curve and eventually leveling off to 0. Again, we can re-express that current function in a little nicer way by using the notation I naught for that original maximum current. And we can clean things up even more by introducing the idea of a time constant. We write it as e to the negative t over tau, where tau is L over R. And the final thing we're interested in doing is finding the half-life. So again, when one half-life has gone by, the current is equal to half its original value. So that's half I naught. And again, this is when t is equal to 1 half-life. And my I naughts cancel. And I take the natural log of both sides. And I realize 1 half is 2 to the negative 1, and I use the properties of logs. It should all seem familiar. I cancel the minus signs. I solve for the half-life, and we arrive at exactly the same formula we did before. The half-life is tau natural log 2, or I could call it L over R natural log 2. Again, I can visualize the half-life by placing cursors into the picture of this function. So I just put a cursor at the max value and the min value, and then we'll put a cursor at halfway between those. That's when the current has dropped to half its original value. That's a 1 half I naught right there. Then I can put in a vertical cursor and say this separation right here is 1 half-life. So this is a really useful thing to remember in the lab. The half-life for when the current is growing is exactly the same number as the half-life for when the current is decaying. So when you're capturing a waveform for an LR circuit on an oscilloscope, if you want to determine the half-life, it doesn't matter which part you choose to analyze. You can look at the time it takes for the current to grow to half its max value or to drop to half its max value while it's in the decaying stage. Finally, we put everything together by applying a square wave signal to an RL circuit. So this is just a way of rapidly turning the power source on and off. And the response of the circuit is to grow exponentially, like we saw in the first part of this video. And then when the signal is switched off, it decays exponentially, like we saw in the second part of the video. And in a typical circuit in the lab, this is happening hundreds or even thousands of times per second. One thing I want to point out about the way the circuit is set up, I'm getting a little bit closer to what actually happens in the lab now. Every inductor has some amount of resistance to it, and I called that R internal. So we model the inductor as an ideal inductor with no resistance in series with a resistor. So when we go to the lab, we're going to have to measure that. The second new feature here is that I'm showing how an oscilloscope needs to be hooked up in order to investigate this circuit. I normally call this second resistor a probe resistor because we're using it specifically to give information to our oscilloscope. So an oscilloscope is not an ammeter. We can't directly measure current with it. We can only measure voltages with it. So I specifically put this new resistor into the circuit so I could hook the oscilloscope across that resistor and read the voltage as a function of time. Well, for a resistor, V is equal to IR, or I could say I is equal to V over R. Either way you say it, the current through this thing is directly proportional to the voltage across it. So what an oscilloscope gives us is a picture of voltage as a function of time, but it's exactly the same picture as the current as a function of time. So the plan in the lab is to lock in this waveform on an oscilloscope, manipulate the oscilloscope cursors to get the half-life, and we could do that while the current is growing, or we could do that while the current is decaying. And then provided that we've measured the total resistance in this circuit and we've measured the half-life, we can use our half-life formula to actually calculate the inductance of any inductor. In the follow-up to this video, which is linked on the left side of the screen, we're going to take these ideas into the lab and measure the inductance of a commercial inductor by applying a square wave to an RL circuit. So if you're interested in seeing how all the practical details work, I'll see you in the lab.